Consider a mass on a spring hanging in equilibrium as shown here. It's in equilibrium, so the total force on the mass is zero. The tension in the spring balances the weight mg. The weight of the mass has extended the spring from its natural length L by an extension x0. The amount that the spring extends is given by Hooke's law. Which states that force is proportional to extension. So that means that mg is equal to k x0, or x0 is equal to mg over k. So that's our equilibrium position. Now let's imagine that the spring is pulled down and let go. It oscillates or bounces up and down about the equilibrium position. Let's think about the energy that it has. It's got displacement x and it's got velocity x dot, and it's got three types of energy. It's got gravitational potential energy given by its change in height. So the gravitational potential energy is mg times x. It's got elastic strain energy, and the elastic strain energy is given by a half k times the extension squared, and the extension when the displacement is x is given by x0 minus x. And finally, it's got kinetic energy, which is equal to a half m x dot squared. So let's combine these to get the total energy. The total energy is given by mgx plus a half k x naught minus x all squared plus a half x dot squared, and because energy is conserved, these terms add up to a constant. So multiplying this bracket out, we have mgx plus a half k x naught squared plus a half k x squared minus k x naught x, and then the final term plus a half x dot squared is equal to a constant. This term is a constant, so we can absorb it without loss of generality into here. We've also got an expression for x0, which is mg over k, so we can substitute this in as well. So we get mgx plus a half k x squared minus k times mg over k x plus a half x dot squared is equal to a constant. So this term cancels with that term, and we're left with kx squared plus x dot squared equals a constant, where we've also absorbed this factor of 2 into the constant. Finally, we can differentiate this expression, and it gives us x double dot is equal to k over m times x equals 0, a second order linear differential equation. And we will come to recognise this particular form as one describing simple harmonic motion.